So I wanted to do a few more examples. These are from chapter 8, of course, in your textbook, starting on page 190 and then actually to 196, I think. So you'll have, if you wanted to follow along in your book, you could find these problems. I think you could view them okay, though. So this first problem, number 15, is the nicotine content of a cigarette related to the tars. Now, I'm not claiming to be an expert on cigarettes, so I'm not quite sure how the whole TARS thing might be connected, but here we have the data. So we'll look at the data. A collection of data in milligrams on 29 cigarettes produced the scatter plot, residuals plot, and partial regression analysis shown. This is typical of some what you might expect to see on an AP exam where, and I told you this before, they don't give you the data, they just give you they give it to you in graphical form, or they might give you some computer generated output, and so we have to just know how to view that. So this question says, part A, do you think a linear model is appropriate here? Explain. So to tell if it's appropriate, you're going to look at a couple things. One is you're going to look at the scatter plot. And I would say that the scatter plot appears to be linear. Now, we have some kind of weird thing going on right here that looks a little different, but other than that, it appears to be linear. The other thing we look at is the residual plot. And remember, what we're looking for is no pattern and not being able to predict what will come next. So at first when I look at this, I think, well, wait a minute, is this a curved pattern? But as you're kind of moving along from left to right, notice that some go down, some go up, not really a fan shape. I really don't know what's going to come next. It could be here, it could be down here. So it's the residual plot doesn't show a clear pattern. You could always mention that, perhaps there's a bit of curvature there, but we're not really sure if there, so then based on that, a linear model is appropriate. I think in the answer key, they say a linear model is probably appropriate. And it's okay to say something like that, when you're looking at it. If there's something, you can make a note of something that you think might be unusual. Part B, explain the meaning of r squared. Okay, well, here is the value of r squared, and so here is what we would say. 92.4% of the variation in response variable, nicotine, let's put milligrams. So 92.4% of the variation in nicotine can be explained by the changes in explanatory variable tar. Okay, so again, that little fill in the blank, r squared percent of the variation in response variable, which is the y variable, can be explained by the changes in explanatory variable. So in this case, it's tar. You're just going to fill it in to give it the context. All right, so the next problem, consider again the regression of nicotine content on tar, both in milligrams. For this, the same example. What is the correlation between tar and nicotine? Well, I already forgot the value. R squared was 92.4%. So you can think of that as 0.924. So to get the value of R, we're just going to take the square root of 0.924, and I get approximately 0.96. I'll go 3 places. So that's the value of R for the correlation coefficient. Now, remember what I said about how when you square root, you're always going to get a positive because R squared is always going to be positive. Sometimes R is negative. When you look back at your scatter plot, it has a positive slope. We can clearly see that. So then R is positive. So you do need to question that, because there will be a time where the scatter plot is negative and you're going to square root it, and you have to remember that R would be negative. Part B says, what would you predict about the average nicotine content? Remember, nicotine was our Y values. It's our response. That are 2 standard deviations below average in tar content. So this is going to have that same relationship that we saw in that problem yesterday. So remember, we had Z hat Y equals R times ZX. So we want to know for this, what would the predicted, what would we predict about the nicotine? 2 standard deviations below average in tar content. So we would take 0.961, and if it's below average, we're going to multiply by -2. And we get -1.922. So we would expect it to be, it would be about 1.922 standard deviations below average in nicotine content. Okay, part C, if a cigarette is 1 standard deviation above average in nicotine content, what do you suspect is true about its tar content? Well, here's the situation. We set up our linear regression equation to predict the response variable, to predict nicotine. We can't just go the other way without creating a new model. So I think you're going to have a problem like this on your homework as well. And it's fine with me if you skip it, but I want to make sure you understand that we can't just say this. It doesn't work the other way unless we come up with a new model. We would have to go back to our data and redo it in order to have it. So this one we're just going to kind of skip, and you'll have one, I think, like that on your homework as well. All right, so it says take another look at the regression analysis of tar and nicotine content of the cigarettes in exercise 15. Write the equation of the regression line. I'm going to copy the information here. So I just copied this from problem 15, and this is where we got the R squared value, but I want you to notice this part right here. So we're asked to write the equation of the regression line. They tell us the constant. Well, hopefully you remember from algebra that the constant on a linear equation is the y-intercept. And this one right here, this 0.065, says it's the coefficient of tar. So remember that tar is our explanatory variable, so that's like our x, and this is the coefficient to that, which means that this is the slope. So you're going to have to be able to look at computer-generated output and pick the equation out of there. So my equation for part A, when it says write the equation of the regression line, so for write the equation of the regression line, we're going to get nicotine hat equals, my constant was 0.154, I'll just go 3 places, plus 0.065 tar. And that's how I would write my regression equation. So I'm just picking that information out. I know that the slope is positive. We saw the graph, so we know that, but also I have a positive slope. So part B, estimate the nicotine content of cigarettes with 4 milligrams of tar. So we're just going to plug that into our equation. And if we wanted to be more accurate, then I suppose we would use the entire coefficient, the entire y-intercept and the entire slope. So I'm going to fill in a 4 there. and we get 0.414 milligrams. Part C says, interpret the meaning of the slope of the regression line in this context. Okay, so remember what we've talked about. As the explanatory variable, which is tar, as the tar increases by 1 unit, which is milligrams, the model predicts the nicotine content to increase by about whatever the slope is, 0.065 milligrams. Okay, so that's what that means. Notice, I mean, it's the same format. The model predicts the explanatory variable is increasing by 1 unit. The model predicts the response variable to, in this case, increase because it's going up by about whatever the slope is. Okay? So, part D, what does the intercept mean? All right? Well, that would mean if there was no tar content. So, if the tar content was 0 milligrams, the model predicts the nicotine content to be about 0.154 milligrams. Now, I don't know if that's possible or not. So I don't know if that's a nonsense answer because I don't know how that works. But I do know that that's how you interpret the y-intercept, okay? Part E, if a new brand of cigarette contains 7 milligrams of tar and a nicotine level whose residual is negative 0.5 milligrams, what is the nicotine content? Okay, so let's start by finding the predicted. So we're going to find the predicted, so 0.154 plus 0.065, and that was 7 milligrams. And we get 0.609. So remember that the residual equals the observed minus the predicted. So they're telling me I have a residual of negative 0.5. We have the predicted as 0.609, and we want to find the observed. So I don't know this one, so I'm just going to call it Nic for nicotine. Minus predicted was 0.609, and you're just literally solving this. So add 0.609 to both sides. So negative 0.5 plus 0.609. So then the nicotine content is 0.109 milligrams. So you definitely want to remember how to calculate the residual, and then just, write that down if you need to, and so that you don't make a careless mistake. All right, next problem. Number 28. Colleges use SAT scores in the admissions process because they believe these scores provide some insight into how a high school student will perform at the college level. Suppose the entering freshmen at a certain college have mean combined SAT scores of 1833 with a standard deviation of 123. In the first semester, these students attained a mean GPA of 2.66 with a standard deviation of 0.56. A scatter plot showed the association to be reasonably linear, and the correlation between SAT score and GPA was 0.47. Write the equation of the regression line. What? They don't have any data. How are we supposed to do that? Well, remember these formulas? And you practice this in a non-contextual problem, but now we have context. So what you're going to do on a problem like this is we're going to identify that what we're going to use for X bar or for the values, because we have to think about, okay, what are we going to use for X bar and Y bar? So in order to know, how do you know what you should use for explanatory and response? Well, what do they say they're trying to do? They believe that the scores, SAT scores, provide insight into how a student will perform at the college level. So notice down in Part D, we're predicting the GPA based on the score. So the SAT score, those are the scores we're going to use for X, because those are explanatory. So X bar is going to be, we had a mean of 1833 with a standard deviation of 123. And then the GPA is going to be our response variable. And we have a mean of, oops, sorry, that should be Y bar is our mean of 2.66. And S sub y, our standard deviation, is 0.56. Now, I'm using the X bar and Y bar and not using, SAT or GPA, because that's what our formulas have. So it's just going to be easier for us to compare. They tell us the correlation is 0.47. So notice they're telling me the value of R. I've got all the stuff I need to build my equation. So part A, when they ask write the equation of the regression line, so I'm looking for this. So I need to know the value of A and B. So I have to start with B equals R times S sub Y over S sub X, because I have all of that. So it's going to be 0.47 times 0.56 over 123. So we get 0.0021. And for accuracy's sake, I'm going to go ahead and leave it to 4 decimal places. All right, so next now we know B, so we need to, we know X bar and Y bar, we need to solve for A. So we have 2.66 equals A plus 0.0021 times X bar, which is 1833. Now keep in mind, again, this 0.0021 was rounded, so I'm kind of doing, using a rounded answer to go on, which is not the best idea, but we're doing it. So 0.0021 times 1833, and I want 2.66 minus that, so I can go second answer to recall that. So I get A is negative 1.1893. Whoops, 3. So part A, the answer, the equation, I'm predicting GPA. So GPA hat equals negative 1.1893 plus 0.0021 SAT. All right, part B, explain what the intercept of the regression line indicates. All right, so let's think the intercept would represent the an SAT score of 0, an SAT score of 0, results, I'm writing this a little different, in a predicted GPA of negative 1.1893. Obviously, this is nonsense. Okay, you can't have that, but that's what it would represent. Interpret the slope of the regression line. Okay, well, we should be getting better at this. So as the SAT score goes up by 1 point, the model predicts the GPA will increase about 0.0021 grade points. Okay, based upon these statistics, how effective, this is like saying how accurate, do you think SAT scores would be in predicting academic success during the first semester of the freshman year at this college? Explain. So what we're going to use this time is we're going to use that R squared value, which was 40.4, oh, that was R, is 0.47. So remember that R is 0.47. So then what's R squared? Well, you just square that. So we get R squared is 0.2209. So what does that mean? About 22% of the variation in GPA, response variable, can be explained by changes in SAT scores. This is very low. Think about what that means. That means there's 78% of the variation in GPA that's explained by something else. So only 22% of this can we say, of this variation can we say is explained by these changes in SAT scores. So because that's so low, my answer would be that SAT scores do not appear to be effective or a good predictor. Okay, I'm just going to tell you what an admissions counselor has said at ONU that I've heard her say. She said that what they viewed the #1 predictor of how well a student was going to do in college was how they did in their math classes. Yep, that's what she said. So I'd say all of you are on the right track. Okay, that was part E, actually. What happened to part D? Oh, sorry, this was part E. I skipped part D. So let's go back. Predict the GPA of a freshman who scored a combined 2100. Okay, so GPA would be negative 1.1893 plus 0.0021 times 2100. And we get about 3.22. All right, so then part F. As a student, would you rather have a positive or a negative residual in this context? Okay, so let's think about residual. Residual is observed minus predicted. So if you had a positive residual, so a positive residual means you did better than the model predicts. I'm thinking you'd rather have positive. You'd rather have a higher GPA than what the model would predict for you because we all want to have a higher GPA. I don't know that I really need to do this entire problem, but I just wanted to point something out because sometimes you get data that might look like this. And notice part A says make a scatter plot for these data. So when you do this, if you were going to enter this on your calculator, and I'm going to clear out L1 and clear out L2, then notice that I have, for age, I have 2 cars that are 1. And so I would have to actually, you know, put both of those as 2. So I have 12,995, and this one was 10,950. And so then I would have to do that, like here I only have 1 that's 2 years old, I have 2 that are 3 years old, and then etc. So when I get down to the 9, I'd have to put in 3 9s and then 1 for each of those. I'd put the prices in L2, make a scatter plot, describe the association. You guys could do all that. Do you think a linear model is appropriate? Computer software says that, you know what, I'm gonna pause this and enter my data and do the scatter plot. All right, so here's my scatter plot. And part B says, describe the association between age and price of a used Corolla. So you're going to say something like, there is it looks fairly strong, I mean, actually we could, oh, you know what, let's calculate this. Let's do stat calc number 8. L1, L2. I'm going to store my regression equation in Y1 and calculate. Okay, so now I can see this. Whoops. Let me drag that down here. Okay, so now I have this, so it appears to be, now I can say strong. Look, it's 0.94. There is a strong negative linear association between the age and price of a used Corolla. I don't even think they make a Toyota Corolla anymore. So, so we have that. Now, do you think a linear model is appropriate? Okay, well, looking at the scatter plot, yeah, it looked pretty good. So if we wanted to know more, we would have to look at the residual plot. And I'm going to go through the steps again for that. So if I go second stat plot, and since I just did regression on this, my residuals are here, are in resid. So second list, and I want resid. Okay, so that's going to set that up. Then I go back to my y equals, and I don't want this one in there. I don't want it to show that, but I do want the equal 0. And now if I go zoom 9, because I have to reset my stat plot, remember we're looking for a random scatter. So, you know, that doesn't look too bad. So here's our residual plot. Okay, so this is the residual plot. No pattern. A linear model is appropriate. And I would want to appeal to the actual scatter plot as well. Okay, so here's what I really wanted to point out to you. Computer software says that R squared is 0.894. What's the correlation between age and price? So if you just did the square root of 0.894, you're going to get 0.9455. However, you have to remember that R is negative. So remember I told you there would be an example. We definitely have a negative association as the year of the car increases, the price decreases. So you want to make sure that you know, that you are paying attention to that. And then explain the meaning of R squared in this context. I'm going to say it, I'm not going to write it. R squared is 0.894. So we could say about 89.4% of the variation in the price advertised can be explained by the changes in the year of the car. So then why doesn't the model explain 100% of the variability in the price of a used Corolla, since they're all Corollas? Well, there's also other things, like it's not just the age, it's the condition of the car, and there's the mileage on the car. So there are other things that would play a part in that as well. Okay, I know this is a long video and I'm not going to do any more, but I just want to talk, this is problem 47, and I just want to talk about computer output. I just covered up what I wanted to see. Okay, that was not a really good idea. But I want to talk about this portion here and how you pick things out. So notice right here, we have r squared. That is the r squared that we care about. Then we have, it says variable, coefficient, and we have all this other stuff that's going to be meaningful to us later, but right now it's not. So we're going to pull this information out right here. If it says intercept, that's the same as like constant. And then this other one, the variable, the calcium variable, is that coefficient is going to be the slope. Notice calcium is on the x-axis, so it's explanatory. And mortality, I mean, haven't even read the problem, but mortality right here is our response. So if I was writing my regression equation, I would have mortality hat equals, the constant is 1676. Since the slope is negative, 3.23, and then the calcium level. Okay, and r squared is 0.43. So then r, if I do the square root of 0.43, I get 0.6557. However, negative slope, kind of a negative line here, this is negative. So you do have to pay attention. There's another example. Okay, so that's it.